Okay, so we continue with the subject of twist-3 GPDs, and the next presentation will be by Fatma Aslan from New Mexico State University.
Okay. So Dr. Walker and I work on twist-3 GPDs and PDFs. I'll talk about and why we study twist-3 GPDs, and then discontinuities in twist-3 GPDs. Discontinuities are found previously in studies where they use boundary check approximation, but in our work we use model calculations and find these discontinuities again. Then, if there are discontinuities, what happens to factorization? And then in the forward limit, we calculate twist-3 PDFs and additionally quasi-PDFs. What is twist-3? It's the order. It determines the order in Q-square at which a matrix element contributes to the physical of a given height process. With the increasing twist, the number of partons which contribute to that matrix element also tends to increase. For example, twist-3 distributions describe two particle correlations, whereas twist-3 distributions also include three particle correlations, such as quark below quark. But it's most advantageous to define the twist in the infinite momentum frame, where the nucleon moves with a high longitudinal momentum and nearly transfers the momentum. In the infinite momentum frame, we can define the behavior, we can define a twist of a distribution by the behavior under the longitudinal momentum boost. Twist-3 distributions are invariant under the longitudinal momentum boost, whereas twist-3 distributions decrease with 1 over p plus. In Bjorkman limit, the matrix elements are mostly dominated by twist-2 operators, but there are motivations to study twist-3 effects. For example, at JLab 12, GeV, twist-3 effects may not be negligible in the measurements of VCS amplitude. And also, like Dr. Broker talked about this, twist-3 distributions also contain quark correlations, which is not contained in the twist-2 distributions. And these quark correlations are related to the average transverse force acting on a quark in a polarized nucleon. So there's a new information embodied in twist-3 distributions, and it is the distribution of that force on the transverse plane. Also, there's a relation between a particular twist-3 GPD G2 and orbital angular momentum of quarks through this sum rule. This G2, twist-3 GPD G2 comes in the permutation of...
It's just somebody who connects.
Oh. It comes in the permutization of gamma perturb matrix element, and in the forward limit, it decouples. There's no forward limit. And its integration, its X integration is 0 to its Lorentz invariance. So this is not to be confused with G2 tilde, which comes in the parameterization of gamma per gamma 5 structure, and this G2 tilde becomes G2 in the forward limit, which is in the DIS cross section, transverse the polarized DIS cross section. And again, through its Lorentz invariance, the X integration is 0. So we calculated G2 in quark target model, where the quark and anti-quark releases a photon or a gluon and recombines it after the interaction. There are several parameterizations, but we use this parameterization. All G's are twist-3, H and are twist-2. And we write the matrix element using the model, and we extract the variable coefficient where G2 comes with H and E twist-2 operators. GPDs. To extract G2, we calculate H with gamma plus. We look at the divergent parts only. E doesn't have a divergent part, and we plot the divergent part of G2. We see that there are discontinuities at X is equal to plus minus C. These points correspond to the nucleon elevation nuclear momentum.
Sorry, I didn't hear that. Why are there discontinuities?
Why are they discontinuities?
Yeah, why are there discontinuities?
our calculations have discontinuities.
Okay, why in your calculations?
What is the mechanism
I
of
think
the
you
events of this? Okay.
I
Are
think
you going from into the department from the left hand side?
I think
What
Jerry means is it does mean that the plus momentum of one of the lines in the diagram vanishes for a certain
Yes, I'll show
Yeah,
that in the
okay.
forward limit.
Yeah.
In the forward limit, I'll show that.
Still not following this at all. You take the matrix element of Q bar gamma JQ in P and P prime. What is P? What is the relation with that? I don't know what a quark target model is. Is it just one quark?
Wrong one.
So you have your target as one quark,
Yes.
and you take that matrix element, one quark.
Uh-huh.
What is the blue one in the middle?
That's my propagator.
Right, she's calculating that
So what
matrix
is the
element
direction?
square.
So what are these?
So that you have an operator that couples to a quark, and the blue one is like
All right.
a spectator, and it gives it some momentum distribution. Wave function, if you like.
Just a question. In a very similar calculation, you can calculate the structure function G2 in the same way. For example, in electrodynamics, for example. At this level, it is the same as electrodynamics.
Yeah.
And then it is known that the structure G2 on this level just vanishes.
Yeah.
And so,
The quarks on shell or off shell?
shell with some mass, with some mass, with massive quarks.
This is non-forward in the logic, so there's
And
It's magnetic moment.
but the integral could vanish, which could give it because G2 vanishes in the dynamics.
Yes.
What shell?
No, I think the forward limit just vanishes.
Oh, it has to balance delta is equal to 0.
The integral over G2 vanishes. That's one of the Lorentz invariant relations that you get. But the x-dependent one is not zero in QED.
G2, okay, I know why it vanishes.
Yes, that's right.
So since there are discontinuities, then we think about what happens to factorization, because GPDs are known to enter the DVCS amplitude in this type of integrals. But these are for twist-2 GPDs, H or E. But what happens with twist-3 amplitude, the type of integrals, they come with combinations, not by themselves. For example, G2 enters the DVCS amplitude with this combination. So we have to check if these combinations are continuous or discontinuous at the poles. So that's, in order to do that, we calculate G2 tilde, again, in the same quark target mode. Again, we write the matrix element, and this time G2 appears with H tilde, G2 tilde appears with G2 tilde, gamma 12, gamma 5 structure. We do the same calculations, divergent parts. We see that, again, at plus minus C, again, there are discontinuities. But in order to check the factorization, you need to look at the combinations. So in order to, for the integrals to be defined, you need to check the poles, if they are continuous. So this combination here, there is continuity here, but at x is equal to C, this combination is continuous. So factorization is fine. This integral is well defined. Same thing happens with this combination. At x is equal to C, this combination is continuous. So factorization is fine. But we think about, we keep on thinking about the discontinuities, like how they behave if we send C to 0, or what happens we use different models. We use also scalar dichotomy model. And what about the forward limit? G2 tilde is a forward limit, which is G2, little G2. So how do the discontinuities behave? As C goes to 0, okay, this solid line shows G2 and dash line shows G2 tilde. As C goes to 0, it's decreasing. The solid line, which is G2, the discontinuities increase. But for G2 tilde, it stays finite and partially cancels upon dx integration. So these are our results for C is going to 0. Another model, we check what happens with another model. For example, scalar diquark model, where the nucleon is represented by a scalar bounded with scalar diquark and a lone quark. And we include the interaction only with the lone quark. Then we again check G2 and G2 tilde. This time, both as C goes to 0, the discontinuities diverge in both of them. So if we compare two models and two twist-3 GPDs, G2 and G2 tilde, we see that G2 is consistent. In the quark-target model and scalar diquark model, the discontinuities are divergent. But G2 tilde gives different results. For scalar diquark model, the discontinuities diverge, and the urban region accordingly becomes the representation of delta function. Since the height increases, the width decreases, it becomes a representation of delta function. So since G2 has a forward limit, little G2, we check what happens to these divergences in the forward limit. Now we calculate GT, which includes G2. Again, scalar diquark model, we use this parameterization. Also, we calculate quasi-GT. Whenever we are calculating PDF GT, we use light flow coordinates, plus minus square. But for quasi-PDFs, we use normal coordinates, 0, 1, 2, 3. And what we expect is longitudinal momentum increases, the quasi-PDF converges to the PDF. And they scale, since they are twist-3, they decrease as 1 over P plus. So here is the plot, this is the quasi, the solid line, and the dashed line is the PDF. Then we plot it with respect to the longitudinal momentum, not x, but longitudinal momentum. Now we see how it behaves if we increase the longitudinal momentum. Okay, I can do this again. This is my nucleus contracted. What happens? So we expect the distributions to decrease with 1 over P plus, 1 over longitudinal momentum, as we increase longitudinal momentum. But we see two different behaviors. We see there's a component here, which does what we expect, but there's another component at x is equal to 0 at k. In this case, k is equal to 0, it doesn't change. So we see that there's a momentum component in the ground state which doesn't scale as the nucleon is boosted to the infinite momentum. Now, if we plot the distributions not with respect to x, not longitudinal momentum, but longitudinal momentum fraction, we multiply that term, the non-scalar term, with pz. Then it becomes a representation of delta function. And we see it as a boosted to the infinite momentum. It becomes a representation of delta function. And okay, this is where the singularities come from in the forward limit. So we write the matrix element using the model, right? Whenever this combination in the numerator gives us a k minus, then our propagator is cancelled with a term in k minus. So whenever k minus appears, we see these divergences. Because this, and then one of the denominators is cancelled, then we are left with integrals of this type, and energy integrals. So for k plus is not equal to 0, this gives us 0 because it's a simple residue integral. Poles are on the same side, so we can close the contour on the other side, so it's 0. But if you look at the general case, the longitudinal momentum, then we have this value. By looking at these two combinations, two cases, we see that there is a delta function at k is equal to 0.
So Jerry can still answer this question earlier.
No, I don't. Yeah, my questions from early on, the first slide are okay.
I mean, where these discontinuities in the delta function come from?
Yeah,
Yeah,
this is going a
this
little,
cancels.
this is going a little fast for me.
Okay.
So, I would say not yet. I mean, this is a very tricky point that has been discussed a lot. And I have seen mistakes in published papers on this very point. And yeah, so this is the equation in 27. This question was first addressed by Yan in the 70s, these kind of delta functions. I'm not sure that this is one of those that he did. I'd have to think about it more. I think it's very tricky. There's been a lot of mistakes in the literature, particularly papers by Chung-Ji, and I just don't know at this point whether that's right or not.
Well, in the non-forward limit, something similar happens. The term where the red arrow points cancels the denominator of the spectator propagator.
Right.
You only have the two propagators for the two coclines.
Right.
And therefore you get a contribution that lives only in the orbital region.
Yeah, I understand the point about the propagators cancel. There's no doubt that that can happen. If I take that expression on the left and multiply it by k plus, suppose in the right corner, suppose I multiply by both sides by k plus squared and integrate over k plus, would I get 0? I guess that's not good. I mean, do k plus cubed on both sides and integrate. Would I get 0 on both sides?
I guess so.
I'm not sure. It must be infinite to me.
Well, I think
It's not
that's
very
a problem that you require. So,
Fine, fine. Yeah, that's what I said before.
Yeah.
I'm happy to read this for later.
Okay. So that's where the delta functions come from. And for quasi-distributions, we get the representation of the delta function as pz goes to infinity. We try this with the other twist-3 PDFs, E and HM. We see the same thing happening. This is the graph of E, distribution and quasi-distribution. Plotted as a function of K, we see that there are two components. This one does what we expect, decreases with 1 over P, longitudinal momentum. And as a function of X, longitudinal momentum function, that component becomes a representation of delta function. We see that by looking at the quasi PDFs. And HL looks the same. What about twist-2 distributions? Now we look at twist-2 PDF, G1, and twist-2 PDF, quasi-PDF. Again, we calculate the PDF using lifelong coordinates plus minus per, and quasi-PDF is with normal, 0, 1, 2, 3. Again, we expect the G1, quasi-G1 to converge to PDF G1, and since they are twist-2, we expect them to be independent of the longitudinal momentum boost. Now, if we plot it as a function of longitudinal momentum fraction, that's where we see the delta functions. We see the quasi-distribution converges to this PDF, but there is no delta function behavior at x is equal to 0. And we repeat that with F1 and H1 as well, and we see that the same thing happens. There is no delta function. Quasi-distribution converges to the PDF, but at x is equal to 0, no such behavior that we saw in twist-3 PDF. And we have two models, chord-type model and scalar-type model. When we compare the two models, none of these twist-2 PDFs have a delta function. And all of them, except this G2 GT in part target mode have the same data function behavior. So just by looking at the general picture, we see that at twist-3 there's something that doesn't exist in twist-2, the data functions. Okay. And when we look at the...
Is there a question?
Yeah.
Then is a problem with this color that was
I guess so. And the statement that you make is for QCD.
Okay. And by looking at the PDFs and quasi-PDFs as a function of longitudinal momentum moment diffraction, we identify these data functions with the momentum components in the union state that doesn't scale as the nucleon is boosted to the infinite momentum. These components, which do not depend on the longitudinal momentum. One question is, do these data functions go away with regularization? What I did until now was only to use transverse momentum cutoff. Using Pauli-Wheeler's regularization. So, okay, this is the solution, and this is the data function. It doesn't depend on lambda, which is the scalar dipole mass. When I'm applying Pauli-Wheeler's regularization, I'm subtracting the heavy mass. So here, without the Pauli-Wheeler's regularization, with the Pauli-Wheeler's regularization, this term is subtracted. Since my data function doesn't contain the lambda, these cancel. But something else happens, which comes again from the K minus term in the numerator. There's another term which becomes a representation of data function this time, as lambda goes to infinity. That's what happens. So divergences are recovered with Pauli-Wheeler's regularization. So what happens if you have data functions? The sum rules involving twist-3 distributions are violated. For example, Lorentz invariance of twist-3 GPDs in zero momentum. All for G's are 0. If they don't take the x is equal to 0 component lambda x, then we will see that these will be violated. And since x is equal to 0 is not experimentally accessible, then if one tries to confirm these rules experimentally by drawing conclusions from the smooth behavior near x is equal to 0 about the behavior at x is equal to 0, they would claim that the sum rules are violated. But these sum rules are the consequences of Lorentz invariance, so there is no need to question them. So if one sees that these sum rules are violated experimentally, that indicates that there is another function. For PDF, same thing. G1 is twist-2, GT is twist-3. If there is one data function here and there is not here, and if we don't take this data function into consideration, then these sum rules won't hold. Same goes here. And for the sigma term sum rule, then this will not be satisfied. Okay, so conclusions are, we found the data function in twist-3 PDFs. By looking at the quasi-PDFs, we see that as longitudinal momentum goes to infinity, we get a representation of the data function. And corresponding to twist-3 GPDs have discontinuities at x is equal to plus minus 16. For example, this was G2, and the forward limit of G2 tilde, where the urban region becomes a representation of data function. So since the combinations which enter the DCS amplitude don't have discontinuities at the poles, there are no problems with DCS factorization. And when we look at the distributions and quadratic distributions as a function of the longitudinal momentum, we can identify these components with the wave functions that do not scale when the nucleon is boosted to the infinite momentum frame. And not taking these data functions into account imply variations of summations at twist-3 level. So what can we do more? We can use other models. For example, current quark uses data function that does address quark cube. And also the composition of twist-3. With the operator product expansion, we decompose the twist-3 distribution into a round-robin checkpoint, a master, and genuine twist-3. We saw that the twist-2 distributions don't have data functions. Any singularity which comes from this integral will not originate from the data functions we found. So that will be some different story. So the potentially data function belongs to the master and genuine twist-3 because Dr. Burkhardt did this previously. He didn't find the G2. He didn't find the data function in G2 in the part-hybrid model, but he did find in H and E. And he found that the data function contributes to both the master and the genuine twist-3. Also, we calculate the x-square moments of the twist-3 GPDs and map out the transverse force acting on the quark in a polarized nucleon. Also, we are thinking about the chiral symmetry breaking in the infinite momentum frame. This is from Dr. Burkhardt's paper with Leonard Susskind, where they explain in this paragraph the chiral symmetry breaking in the infinite momentum frame. So they say upon boosting the system to the infinite momentum, the partons would all become very far from eta is equal to 0, which is x is equal to 0. And since all the vacuum activity takes place at x is equal to 0, it seems very curious how these partons could feel what's going on at x is equal to 0. So we think there might be a connection with our data functions, because there's a momentum component in the nucleon state which doesn't scale as the nucleon is boosted to the infinite momentum frame, and that these two can be related. They don't go away. They are still there. Only with Pauli-Rudolph's regularization, but then we recover something else again, which has the same origin, K minus.
The light from finder dimensional regularization can only be done on the transverse component, and so it behaves in many ways similar to transverse momentum.
I'd like to make a general comment regarding factorization. Factorization assumes some kind of separation of momenta in hard and soft, and where soft means that there's some hadronic scale, and the whatever virtualities or invariant map of the virtualities of the partons, or if you like, in the light from the time order description, the invariant masses of the bound states are limited to values of the order of that scale. And only then do we have factorization. So that there is a very basic assumption of softness of the object describing the hadrons. Now, the models you used, which is the quark target model and the scalar diquark model, they have no notion of softness other than some cutoff you might put in. And therefore, it's not surprising that you get jumps in G2, for example. And but physically, they should be regulated by a limitation, say, on the invariant masses of the configurations or the virtualities of the lines that has to come from physics, and that's not part of your simple models. And if I might add, I mean, you can get jumps even in the twist-2 GPDs in this way. I mean, we did a calculation, the Chiral-Borg-Soliton model in 1997, where which is basically a kind of dressed quark model. And then if you implement your cutoff, say, through Pauli-Villard regularization, you find jumps at x equals chi, because you admit invariant masses of the system that are of the intermediate states that are of the order that diverge like 1 over x minus psi as you approach the transition point. And you have to exclude them on physical grounds. And if you choose a physical regularization like invariant mass cutoff or virtuality cutoff, they will go away. So I mean, it's interesting that you find the cancellation of these divergences already with the point life model, but that's just the first. That's just the first step. So for real factorization, we need to model the soft parts in a way that they're actually soft, and that's the major challenge, I think.
Well, since you mentioned the invariant mass and the regularization, invariant mass regularization actually violates Lorentz invariance, and that would manifest itself here in the Lorentz invariance relation being violated.
I don't believe that cannot be cured or turned around in the same like with the angular conditions that you impose Lorentz invariance, and then you get some, say, you can calculate the Lorentz invariant restoring term from your regularized invariant mass regularized distribution function.
But if you calculate, if you're done calculating your PDF at finite x, then you actually need the delta functions to restore the Lorentz invariance.
Yeah, that's quite right. The regularization is a crutch. I mean, it's a very primitive way to model the bound state, and it works only in the quadratic region, and it's quite possible that for strict x equals 0. The partons that are left behind, if this thing accelerates, we need to figure out the regularization to independent consideration.
Yeah, let me continue with Kristen's point, if it's okay, because I think he's really right in this case. In scalar diquark model, people have made calculations by putting in form factor. And this could lead to all sorts of trouble. However, you really want to think in terms of the light front wave function. To get the light front wave function from the Feynman diagram, you have to integrate over K-. So putting in a form factor, but and you have to have a well-defined wave function. And one way to do that is when you integrate over K-, you have to get the same answer when you integrate over the upper half plane and in the lower half plane. You got to get the same answer. And that's not so easy to do. With certain mathematical forms for the form factors, it works out to get the same answer integrating over the left-hand plane and the upper half plane and the lower half plane. And so you get a well-defined wave function, which has none of, well, I don't know about this case. I don't want to say anything. But for the cases that we looked at, everything was smooth. And this is in the paper by Mary Alberg and myself. This has been on the web for a few months. This is, I think Kristen is right, and I think the problem is solved. I don't know what the answer is.
Well, if you put in a form factor, that's what she showed, that singularity actually goes away, only to be recovered slowly as you send the regulator mass to high values.
Yeah, but in this case, we want to put in a form factor. We want to make this model reasonable, so you should reproduce the measured electromagnetic form factors, for example. And then the regulator has some physical meaning. You can't take it to infinity and still get a reasonable form factor.
Right. If you do that, then you don't get delta functions, but you get peaks.
I don't know how you can say that because I don't think you've ever used these particular form factors. I don't think the answer is no.
Well, that's for the form factors.
For the form factors, there's no problem. You can easily get form factors.
Just a couple of comments. I mean, if you see the delta functions or
discontinuities in a perturbative QCD calculation. It's still not clear to me why one should not see them in reality. Another remark is actually on the factorization. I mean, the statement about factorization, it's not a proof of factorization. It's just a necessary requirement in order that factorization can hold. To put it the other way around, if in this linear combination of the GPDs, discontinuities would not cancel in this model calculation, I would be extremely worried. I mean, it's not a proof that twist-3 factorization holds to all orders, but it's just a necessary requirement, and it's kind of reconfirming that everything falls into its place if you look at the proper linear combination. And normally, these delta functions in the pattern distributions imply that in the dispersion relations for the corresponding amplitudes, we have to have subtraction constants. And I think for G2, I would very much suspect it will contradict what we know of the range behavior. So for E, I know that it is an old problem. It might be the case, a very specific case. But for G2, I'm personally very skeptical because this would need that would essentially mean that the normal perturbative analysis of large energy behavior is wrong. Different behavior. And therefore, I'm kind of suspicious of that. And in this slide, front frame calculation, with an infinite amount of subtleties. But if you, for example, calculate in the BF-tail like framework, I don't quite see how in the case of this functions like G2, you would get a subtraction constant, because that will mean that you change the energy.
Comment on G2.
G2 is fine.
Shows
you have shown that the G2 is also possible.
In the scalar dipole model, but in the Cork target model, G2 was the only one that didn't have a delta function. So it's consistent with what you're saying.
Yeah.
G2 had a delta function, G2 did not. E had one, H longitudinal had.
Okay, but that is fine, but in any case, I think that the way to look at that is essentially to study the range behavior of this amplitude. Because that is a very, these delta functions are just subtraction constants. Yes, and actually the equation to calculation, but imagine these delta functions are there, so what would be the scale dependence on this one, on this coefficient?
You say because you are sure that this capacity is not.
Well, I will not, I will not. I think it is. I will very much surprise it. Because, as I say, the usual argument I think is just either you just know that this amplitude decreases with energy, and if they decrease with energy, you can write a dispersion relation without subtracting constants, and then you are there. So if you say that there is a delta function, you must have a subtraction constant, and that's a very strong state. Yes.
Because it says unsubtracted dispersion relation.
Oh yeah, but you need subtraction constants exactly in the situation when you know energy behavior is fast. Yes.
Let's not get hung up with the Burkhardt cutting ensemble, because the Cork target model is just fine. That was the only exception that we found, more or less.
Yeah, but okay.
Otherwise, it seems to be a genuine twist-3 type thing that we run in these delta functions.
So you were saying that generical behavior of twist-3 scattering amplitude high energy is different from what.
I'm not saying scattering amplitude,
but it's correlated.
I'm saying correlated. She also showed that in the PBCS scattering amplitude, this thing cancels, because it's not one GPD, but a specific linear combination of two GPDs that ended. And in the Cork target model, for that specific linear combination, the discontinuity is exactly cancelled.
Shouldn't it mean that we simply use bad definition? maybe we just have to redefine everything in terms of physical amplitude.
So maybe I can remark. So there is Andrei Balitsky and Dieter Müller derived the evolution equations for this E tilde, so the pure twist genuine, so twist-3 part. And they write a footnote. Actually, we make evolution for x times E to cancel out the delta function.
X times E, yes?
Yes, he has a delta function.
So E is probably, as I say, E is probably. Okay. Well, we did this one. This was done by Tunji.
I mean, just on a technical side, following up on your suggestion, what we do is write this triangle diagram for the coordinate in a dispersive form and see what the high energy behavior is. Then you can see your Reggie, like we suggest, non-regized
you will be
exchanged in the T channel, so you see what energy, what high energy behavior you get.
Okay, I'm not an expert on this, but in the case that you recaptured of it listening to us, he could be the right person to ask what is precisely known about the range of behavior.
I don't know much what it means, but in the language of Reggie's theory, they correspond to chain-coincident fixed codes.
Yes, exactly. And the question is whether they're similar to the perturbative theory or not. As I say, E is a special case, but I don't know. In simple physical amplitudes, that may be the before.
Maybe can have slight different comments. And when you go dealing with the high twist matrix element, whether it's G2 or psi bar gamma per psi, but by definition, you can't perturb that is ultraviolet blue. And then you have to renormalize it. And when you renormalize the operator mix, then for example, we will mix the psi bar and F plus per psi. So then, depending on what if you take the P plus go to infinity before you mix it, it's oh, I don't have mix. But if you do correctly, P plus external variable, you keep the P plus, then you have to mix operator together. Then you will find the correct behavior, and you take whatever P plus to do out. So I think we have to be careful here and how we draw the conclusion.
That's also true. But as I say, this way of calculation, there are many ways to.
The delta plus term is not surprising because that's exactly the zero motion.
Yeah. Yes.
So actually, Yuri is listening to us. Unfortunately, we cannot hear well discussion. So the private message says small x asymptotics is double logarithmic, not a simple regularization. However, what exactly was Volod asking?
When he reduces the subtractive constant in H8.
Sorry everyone. I can hear like every other word in the discussion. I can hear the speaker, but I cannot hear the discussion very well. That's why I'm asking.
Yuri, the question that's been discussed is how solid is the statement that we can have delta functions in twist-3 distribution. Do you hear me?
Yeah, I can hear you. I'm not sure I know the answer. I haven't thought about it. I mean, I thought you were asking about Reggie asymptotics, so one can certainly.
These delta functions are related to subtraction constants in dispersion relations at amplitudes at high energy.
Yeah, no, I heard what you said. I'm not sure I can comment intelligently. Certainly looking just at small x asymptotics of, say, G1, but you're looking at twist-3, right? I'm talking about twist-2, I guess. There's nothing funny there. We didn't see any delta functions.
I mean, yeah. Maybe you can think further about this question or discuss it along your offline.
Yeah, sure. Okay. Sorry.
I think we need to move on. Let's thank Aslan. Last word is